Now, how do we generate these hash codes that have the property that they're similar for nearby points? So locality-sensitive hashing does it in one particular way. So let's say I have this little collection of documents. These are documents over a 3-word vocabulary: dog, cat, lion. Let's say I want to find near duplicates, and specifically I'm interested in finding duplicates of A, right? So I want to find points B and C. I want to generate hash codes in such a way that B and C land in the same hash table buckets as the document A, and I'm drawing them on the surface of a unit sphere, right? We talked about that in the vector space model. So they're all unit length. That'll just make the math a lot easier. So the way that LSH operates is you take the space and you start cutting it with hyperplanes. So you take random hyperplanes and run them through your space. So basically what this means is, now my hyperplanes are, for simplicity, you can assume that they all go through the origin, right? So imagine this is an octant of a sphere, right? So what I'm doing is I'm taking a hyperplane and cutting the space through the origin at some angle, at some orientation. So it's going to go through the origin, but the angle is going to be different. And depending on what angle I position this hyperplane in, I'm going to get a cut on the surface of my hypersphere. So for one particular hyperplane, I might get that as a cut. So that hyperplane is going to cut my space into 2 half spaces, and I'm going to arbitrarily call one side positive and one side negative. So in this case, everything that's below this boundary is going to be positive, everything that's above is going to be negative. And the way that I'm going to use positives and negatives is all the points that end up on the positive side of the hyperplane, I'm going to set their first bit, the first bit in their hash codes, to be 1, and for the negative side, I'm going to set it to 0. Right? So the points A, B, and C are going to have 1 as the first bit, and the point E and all of the other points above are going to have 0 as the first bit. But I'm not going to stop here, I'm just going to keep cutting. So I'm going to have a red hyperplane, and that will be used to assign the second bit in the hash code. So in this case, point C will get a second bit of 1, points A, B, and D, and E, they'll all get the second bit of 0. Okay, and then I'm going to keep doing that with a green hyperplane. And once I've done that, once I have a few hyperplanes, what I've done is I've actually partitioned the space into disjoint regions, right? And these regions are spatially proximate, in a way, sort of by definition, because I'm cutting the space. What ends up in one region is a chunk that lies in a particular corner of the space, so to speak. And I can use the result of this cutting to generate the hash codes based on the bits that I assign after each hyperplane. So the point A, for example, with 3 hyperplanes like this, it would get a hash code of 100. Why? Because it's on the positive side of the blue, and it's on the negative side of the red hyperplane and the green hyperplane. So point A would get a hash code of 100, and so would point D, and so would point B. Okay, and point C would get a hash code of 110 because it was different. It was so it was on the same side of hyperplane of the blue hyperplane and the green hyperplane, but it was on a different side of the red hyperplane. So its hash code is going to be different in the middle position. I'm going to get 110 as opposed to 100. And then what I'm going to do is I'm going to take these bit strings and use them as hash codes, as keys into the dictionary. So I'm just going to insert them in the hash table, and what's going to happen in that hash table is for a key of 100, I'm going to get documents A, B, and D, and then C is going to land in a different bucket. Okay. Now you look at this and you start realizing, okay, so A ended up in the same bucket as B and D, so B is good. B was nearby to A, so it's actually a good. It's a true positive in a way. It's a near duplicate, and I found it in the same bucket. D is a false positive. It was far away, but just by positioning of the hyperplanes, it ended up in the same bucket as A. Now that's not a problem, and the reason that's not a problem is, remember, LSH has a second step, right, where you go into that bucket and then you do exact comparisons within that bucket. So when I do the exact comparison, I'm going to figure out that D is actually pretty far away from A. Right? So I can remove that false positive with a second step. But the point C, I'm never going to get, because that ended up having, it was on the wrong side of the red hyperplane. It got a different hash code, landed in a completely different hash table bucket. So how do I get around that problem? How do I find C? And the solution is you repeat the same process with a different set of random hyperplanes. So here's my space again, exactly the same space, exactly the same documents on the surface of the hypersphere. I'm going to generate 3 different hyperplanes, H4, H5, and H6, and these hyperplanes will partition the space differently. I'm going to have different regions, so now A is going to have a code of 0, 1, 1, because it's on the 0 side of the blue, it's on the 1 side of the red, and it's on the 1 side of the green, and C happens to have the same hash code. So when I insert them into a hash table, they will collide and they will end up in the same bucket. But now B is going to be in a different bucket. Okay? So for code 0, 1, 1, I'm going to find A, C, and E, and B is going to be in a different bucket. Okay? So the fact that B is different here is not a problem because I've already found it in this case. So the way the process works is you do it multiple times with L different hash tables, and you collect all the duplicates that you find in any one of the runs. So this way you will find B, you will find B and C, and you will eliminate D and E when you do your exact comparisons within a bucket. Okay, so is that fairly clear how it works? Any questions at this point? Yes?
What if the first time you find all the duplicates already in the same bucket,
okay.
But you need to stop at some point?
So the question is, what if the first time you found all the duplicates? You don't know that. When you're doing this process, you don't know if you found all the duplicates or not. So you cannot stop after the first hash table. The way this works is you do it a fixed number of times, maybe 20 times with 20 different hash tables, and you look at the buckets in all 20 cases. So no, you don't stop early. You cannot.
If you find 20 times, there will be possible you don't find all the duplicates.
So it is, the question is it possible that you do it 20 times and you don't find all the duplicates? Yes, it is possible. And we'll talk about the probability of that happening in a couple of slides. So you can measure, you can put an error bound on that. You can measure how often that will happen. Okay, great. So that's the process. Now, how fast is this compared to other ways that we know of finding near duplicates, right? So what's the computational cost of LSH? You have n points in space, n documents in this case. Each document is d-dimensional, and when we're talking about documents, they have sparse representations, so d is just the average document length. It's the average number of non-zero entries in the vector. Now, LSH also works for non-sparse data, for real-valued vectors, which are dense. In that case, d would be the true dimensionality of your data, because all the dimensions are non-zero always. But if you have sparse data, then d doesn't have to be the full dimensionality, right? So it doesn't have to be 10 million. It can be whatever the average length of the document is. So if it's a tweet, you're talking about 20, as opposed to 20 million. Let's say we're generating k-bit codes, so that means that every time we're going to have k hyperplanes cutting through the space. So it's going to take us d times k operations to find the right bucket for document A. And why is that? It's because to figure out which bucket A lands in, what we need to do is we need to take A and do a dot product between A and each one of the normal vectors for the k hyperplanes. So if h1 is the normal vector for the first hyperplane, I'm going to do A transpose h1, A transpose h2, A transpose hk. Each dot product is going to have d scalar operations in it, and I'm going to do the k product. So it's dk to find the bucket where the point A lands. Now, once I land in that bucket, there's going to be some documents, and I'm going to compare my point A to all of the things that land in that bucket. So, how many documents are there going to be in the bucket? Well, you don't know. Some buckets have lots of documents, some buckets have few documents. But you can get an average figure for that. And the average figure comes quite simply. You know how many points you have. You have n points. You know how many hyperplanes you have k of them. If you have k hyperplanes, this means that you will have 2 to the power of k regions in space, because that's how many intersections of half spaces you can possibly have. So if you have k bits, you're going to have 2 to the k possible hash codes. Right? So the total expected number of points in that bucket is going to be n divided by 2 to the k. That's the expected number of collisions in the bucket in a single hash table. And then what I do is I do the comparison of my query point A to all the documents in the same bucket. There is n over 2 to the k of them. Each comparison is going to take d scalar operations, so it's going to be dn 2 to the k. So that's the cost of doing the comparison. So I have two parts to this. I have dk, which is finding the bucket, and dn over 2 to the k, which is comparisons inside the bucket. And you see, with k hyperplanes, that's where the saving comes from. I do k dot products with the hyperplanes, but I cut the search space by a factor of 2 to the k. So that's where that's where the power of the LSH comes from. You are dividing the space into an exponential number of buckets. And then, of course, don't forget, I have to repeat everything L times. So all of those estimates, I'm going to multiply them by L. So if you put it all together, you have the total number of operations is approximately LDK, so that's for finding the buckets in L different hash tables, plus LDN over 2K. So that's for doing comparisons in those L buckets once you find them. So that's the total number of operations. When you do complexity analysis, typically what you care about is how does it scale in relation to n, where n is the size of my data set, right? Because that's really what you measure by. So if I give you a billion documents and ask you to find duplicates in them, you care about n. You don't really care about the other factors. Now, and to get a complexity for that, you need to somehow tie the k to n, right? Because if you just say that k is a constant, then this has complexity O of n, which is not desirable. But suppose that you set k as something on the order of logarithmic in terms of n, right? So if k is logarithmic in terms of n, then here what you have 2 to the log of n, which is just on the order of n. So this part becomes a constant effectively. So you will have a constant number of comparisons inside a bucket, and you have log of n coming in here. So the overall complexities of this is going to be on the order of log of n. Okay, so it's important to be aware LSH is often misrepresented as having a constant query time. So people throw around numbers saying LSH has complexity O of 1. It's not really O of 1. It's only O of 1 if you fix k at a certain number. And then this part will come to bite you. So people often forget about that part. So it is not constant. It's actually, the best you can do is approximately logarithmic in the number of data points. But that's really good, because remember, what are we comparing this to, right? How else could we do this? Well, we could do it in the brute force way. Take the query point and compare it to every other documents in the data set. And that's going to have a dn operations. D is the number of terms for each dot product, and I'm going to do n different comparisons. So that's O of n complexity. And then if you do an index, the complexity turns out to be around the square root of n. right? And you should be able to work it out by now. The way you work it out is think about how the index works. I'm going to take my query point, A. That point has a number of words. In fact, it has D words. So I'm going to pull up D inverted lists and do an update of the scores on that. Now, how many entries does each inverted list have? We can compute it from the total number of postings in the matrix. So we have n documents. Each document is of length D. So n times D is the total number of non-zero entries in my index, total size of all inverted lists, right? And then I'm going to divide that by how many inverted lists I have, because I'm looking for the size of the average inverted list. And how many inverted lists I have, that's the size of the vocabulary, V, and we have Heap's law that tells us that the size of the vocabulary is approximately the square root of the total number of terms in the data set, right? So the total number of terms is ND. You have a square root of ND, so you have ND over the square root of ND. So you end up with a complexity which is d square root of nd. And if you're just looking for complexity in terms of n, then it's proportional to the square root of n. Right? So compared to that, log of n is really, really attractive. It gives you really, really fast time for finding similar documents to your query A.